Hello students, welcome to PH107 Quantum Physics and Applications. Today I am going to introduce you to a new topic called statistical physics. So let's uh, ask a very basic question: what it is statistical physics and why we need. Okay, so till now I'm sure that you are experts on how to handle or how to deal with the dynamics of a single particle, both quantum mechanically as well as classically. So for that purpose, either we can solve Newton's equation of motion or Newton's law to know the dynamics of a classical particle, or equivalently we can solve time independent or time dependent Schrodinger equation to understand the time evolution of a state of a quantum particle. However, this is far from the reality. So what we really want to do in real life, we want to know the physics or the dynamics of a particle in a microscopic world which contains many particles, and not to mention that these particles are interacting with each other. So if you think that the knowledge that you have gained so far, either by solving the Newton's equation of motion or time dependent or time independent version of the Schrodinger equation, to describe the macroscopic world, it is going to be very difficult. Okay, so let's take a simple example. What you need, let's assume that we want to describe the motion of air molecules, which contains oxygen, nitrogen, carbon dioxide, or any kind of gaseous particles in a closed room. For that purpose, we need to track, or we need to understand how 10 to power 23 particles are behaving, or how they are evolving in time. Okay, and this is a huge number. 10 to power 23 is a huge number, and this number comes from the Avogadro number. So if you try to describe the motion of each molecule, which will take clearly all the computational power of any conceivable machine, as well as the efforts from the investigator. Therefore, we need to find a simple way or appropriate theory in a very simple language which allow us to assess the collective behavior of large systems such as this one, 10 to power 23 particles in a closed room, without having to track the evolution of individual particle in the system. Okay, so what is the purpose of the statistical physics, or the purpose of this particular present lecture and the coming few more lecture is to explain the microscopic, or we could call as a collective properties such as energy, momentum, or thermodynamic properties or thermodynamic parameters such as pressure, volume, temperature, magnetization, etc. of a large collection of particles. In a more specific way, we are interested in finding the number of particles, which we are going to represent by D and E, in the system with energy range between E and E plus dE. Therefore, the term we are going to use for a large collection of particles is a system. Okay, so our task is to find the number of particles D and E. This is an important quantity that we are interested to describe the collective behavior or the thermodynamic properties of a large collection of particles. So let's see how this property we can calculate or estimate. But before that, let's ask how this property depends on different behavior or properties of the system. So the number of particles between E and E plus dE. So obviously this d and E depends on the total number of particles in the system. Let's call as n. And little less obvious is that d and E depends on two other important factors. The first one is the number of available energy states between the energy interval E and E plus dE. And the second crucial important quantity in which D and E depends on the probability that a particle can occupy a particular state. So D and E depends on one important quantity which we are going to denote as G of E, density of state, which is going to give us the number of available energy states between the energy interval E and E plus dE. And the other quantity is going to be described in terms of the probability of a particle occupying an available state in an interval E and E plus dE in terms of the probability distribution function. Therefore, the total D and E, the number of particles between E and E plus dE, can be written as the product of GE, which is density of a state, and the probability distribution function Fe times dE, which is the energy interval between E and E plus dE. Okay, so let's have a closer look on density of state. So for that purpose, we are going to consider an example of many particles in a three-dimensional infinite potential box. I'm sure that you have learned what is three-dimensional infinite potential box quantum mechanically. So let's assume that we have a large number of electrons, and these large numbers we are going to express by the Avogadro number Na in a macroscopic three-dimensional potential, and this three-dimensional potential has a box with box size 0.1 meter. Okay, so now once we know the value of L, we now know the Avogadro number, we can easily estimate what is the energy. So the available energy states, assuming there are no interaction between the particles, is of the form, remember that this is what we have written. So E is equal to, going back from your particle in a box lecture, the total energy is written as pi square h cross square over 2ml square times nx square plus ny square plus nz square, and these individuals are coming from one each dimension. So since we are considering three-dimensional infinite potential box, so each one is coming from one dimension. So if you substitute the value of pi h cross to m, here we are talking about the electron with this Avogadro number, and the length of the box is given. So this will come out to be 3.76 times 10 to the power minus 17 times these numbers times EV. Okay, now you could clearly see that the energy spacing between energy states are going to be of the order of 10 to the power minus 17 electron volt, which is a very tiny number. Okay, so the available energy levels can be are very closely spaced, and therefore we can treat them as a quasi-continuum of states. So that's why we need to invoke the notion of density of state G of E when we are talking about the microscopic world, because we do see that within the given energy range, the energy spacing is going to be 10 to the power minus 17, and if you say that I am interested the number of states in the energy interval of 1 eV, there will be n numbers of states 10 to the power 17 energy states are going to occupy within the energy range of 1 eV. So that's why we can call these energy states as a quasi-continuum of states. Okay, but still we are using not continuum but the quasi-continuum, because the number of states within a certain energy range is finite, though quite large. Now let's have a closer look at f of e, which was a probability of probability distribution function. So the need for f of e, or the probabilistic description of an ensemble, arises because first we have a classical uncertainty due to the fact that we cannot determine the state of every particle at all times, because we are interested in a collective behavior. And the second one, that we have a quantum mechanical particles in some situations, and therefore we have an inherent uncertainty of each individual particle's quantum states, which comes from the uncertainty principle. Okay, therefore this f of e, this probabilistic description, depends on the particle's characteristics. What are the particle characteristics we are interested. So this depends on what kind of particles we are talking about, whether the particles are classical particles. Classical particles are those particles which are distinguishable. We will see in a moment that which are the classical particles, which need not obey Pauli-Exclusion principle. I am sure that you know what is Pauli-Exclusion principle. I am going to recap in a moment. Are quantum particles. So one kind of quantum particles are the bosons. These quantum particles are indistinguishable in nature, which do not obey Pauli exclusion principle, but they are indistinguishable, unlike the classical particles, which are distinguishable as well as they do not obey the Pauli exclusion principle. Here, they are indistinguishable, but they also do not obey Pauli exclusion principle. Are fermions, which are indistinguishable as well as they have to follow the Pauli exclusion principle. So now let me ask a simple question. So we know that quantum particles like bosons, fermions obey either integer or half integer spins, which we will see in a moment. So now my question is, are there particles which obey fractional quantum statistics? If yes, what are they called? So let's recap what we have learned about the Pauli exclusion principle. So Pauli exclusion principle is kind of based on empirical evidence, and which come from, let's say, the periodic table of elements, and which states that it is impossible for two electrons which are fermions in an atom or molecules to have the same values of the four quantum numbers. What are the four quantum numbers? N as principal quantum number, L as angular momentum quantum number, Ml as the magnetic quantum number, and Ms as a spin quantum number. So it is impossible for two electrons to have same value of four quantum numbers. Okay. Or in a more general way, two identical fermions, particles with half integer spin, of which electrons is an example, cannot occupy the same quantum state simultaneously. So if you say that you have two fermions which are having or which are occupying the same quantum state, it means that these two fermions uh, do not have all four quantum numbers identical. Okay, the principle does not apply to the particles with integer spin or bosons, as we have seen, so that any number of bosons can occupy the same state. So let's go and refine our understanding in a more rigorous way by stating that the total wave function for two identical fermions, such as two electrons, is antisymmetric with respect to exchange of the particle. What it means that the wave function changes its sign if we exchange the space and spin coordinate of any two particles. So let's have, this is the total wave function for two fermions, where r is the spatial coordinate and the sigma is the spin coordinate, and if I want to exchange r1 by r2 and sigma y by sigma 2, it will give me minus sign because this is antisymmetric in nature. So this is what I have done. So I have exchanged this coordinate r1 sigma 1 by r2 sigma 2, and here I will get minus sign, and this shows that my total wave function for two fermionic particle is antisymmetric in nature. And this is general statement. If you talk about not only two but in general n fermions wave function, it has to obey this antisymmetric property. Now if we talk about the bosons, and let's say if you have a two identical bosons, then their total wave function be symmetric in nature. So let's write down the two bosons wave function as again psi r1 sigma 1 and r2 sigma 2, and if I exchange it, I'm not going to get minus sign but I'm going to get plus sign. So this shows that the total wave function is symmetric in nature, and this is true not only for two bosons but in general n bosons. Okay, so what we have seen that the number of quantum particles that can be placed in any state depends on spin degrees of freedom of the particle. Okay, so to estimate or to have some idea about f of e, what we need, we are going to dedicate the coming lecture and this rest of the lecture is to estimate how to estimate this f of e, and the purpose of the rest of this lecture or the next lecture is to estimate f of e for the classical particles as well as for the quantum particles. So now the question comes, how to calculate f of e? Okay, so Let us analyze the question further. For a given fixed energy E of a system, how do I know what is d of n of E, which was the number of particles between E and E plus dE? Or let's start with f of E and we will handle the other part of this important quantity, which is the density of a state, later. Okay, so let's consider a very simple example for this purpose. So here what we are going to consider two particles, and these two particles can occupy three states. So let's say that we have a system of two particles with total energy 2E. The energy states available to the systems are 0, E and 2E, and the degeneracy of these states are 1, 2, 1 respectively. Let me explain in a simple way. So here is my energy spectrum. So here is my energy E is equal to 0. Here are two-fold degenerate energy states E, and here is a single fold or non-degenerate energy state 2E, and now I have a two particles whose total energy is 2E. Okay, so here are the state index I am going to represent by I. So first states total energy 2E, state degeneracy I am going to describe by GE, which has 1, or let's say no degeneracy, okay, or single fold degenerate. Now my state 2 has energy E and the degeneracy is twofold, because you can see that there are two states with energy E, and now my third state is of energy 0 and the degeneracy is 0. And now I'm going to distribute the two particles so that are in a manner that the total energy of the particles will be 2E. Okay, so let me arrange, or let me make a different arrangement of the two particles for a given energy. Okay, so what are the different ways in which we get the total energy of the two particles to be 2E in this configuration? Okay, so this is one condition. I can have one particles with 0 and another particle with energy 2E, and I'm going to use two different colors, and in the beginning I'm going to consider a classical particle which are distinguishable. So I'm going to have two labels, one with red and another with blue. And the other possibility, because these are the distinguishable particle, so I can have another scenario where my blue particle has total energy 2E and the red particle has total energy 0, so that the total energy of this system again is 2E, because 2E plus 0 is 2E, and in this case also my total energy of the system 2E plus 0 is 2E, where my red particle has total energy 2E and the blue particle has total energy 0. Now what are the other possibilities? The other possibilities are that one particle can have energy E, another particle can have also energy E. Since these are distinguishable particles, now I can put this blue particle this place and I can put the red particle to the blue place. So this is another configuration in which I can have another one. Now what are the other possibilities? Other possibilities are that both the particles can be in the same energy states, or this energy can be also in the same energy state. So these are, let's say, possible arrangements in which the total energy of the two particles are 2E and these particles are distinguishable in nature. So what are some of the definitions or the terminology we are going into this part of this course of statistical physics is microstate, ensembles, and the microstate. So what are the microstates? So individual these states we are going to call as a microstate. Now the whole box in which you have a number of microstates are going to be called as a ensemble, and the total one is called as a microstate with total energy 2E. Okay, so this is one configuration. So what are the meaning of the configuration? So this is the configuration I'm going to define as follow. So this is first particle with 1, then there is no particle, then the third energy state has one particle. So this is 101 configuration. This is another is again 101 configuration. So these two configurations are identical. Now this configuration will be your 020 because there is no particle here. Second energy state has two particles, the third has no particle, so this is 020. This is again 020. This is again 020. This is again 020. So these kind of uh, uh, representations we are going to call as a configuration. Okay. So the a priori probability of occupancy of all microstates is equal, so that 0 to 0 configuration is twice as probable as 101 probable. We can see that there are four possibilities or four chances that 0 to 0 configurations are 1, 2, 3, 4 here, whereas 101 configurations are occurring two times. So the probability of having 0 to 0 configuration is twice as probable as 101 configuration. Okay, so we are discussing the classical particles, and in this example we have assumed implicitly that these particles are distinguishable. That's why we have used two different colors, red and blue, and which do not obey also the Pauli exclusion principle. So you could see that these microstates here, fifth and sixth, are not fulfilling the Pauli exclusion principle. So both the particles are having the same energy states. Okay, now these are the possible configuration for 2e total energy, and now let's see which configurations are allowed and which configurations are not allowed for particles or for quantum particles. So first we are going to consider bosons, which are indistinguishable in nature, but they do not obey Pauli exclusion principle. So once we say that they are indistinguishable in nature, it means that we are not anymore allowed to have this labeling of red and blue. They are identical, so red and blue and red configurations are the same one. So here is the one where I have changed the color of red by all blue. So these are the one for the bosons, and let's see which are the identical one. So these are the identical ones, so this I can cross it out. Now this is the identical one, so this I can cross it out, and this is the identical, these are the ones. So we can again see that your 0 to 0 configuration in this case is thrice as probable as 101 configurations. Okay, so this is 101 configuration, and these are your 0 to 0, 0 to 0, 0 to 0 configuration. Okay, and these are probable because again your bosons do not obey the Pauli exclusion principle, so these are possible for the bosons. Okay, now in the case of fermions, again we have one more restrictions. First of all, they are indistinguishable, so this will be cancelled it out, this will be cancelled it out, and like in boson. Now this is not possible in the case of fermions, because two fermions or two electrons cannot have the same energy states. So these are crossed out, and in this case we can see that the configuration 0 to 0 is as probable or equally probable as 101 configuration. So we have seen that as you change the nature of the particle, we can see that the probability of different configuration changes. This is the first important lesson that we have learned. Okay, so now let's state the general problem for classical as well as for the quantum particles. Given a system with a set of energy states, in particular case we have considered 0e and 2e, each with degeneracy 1 to 1, with a fixed amount of energy 2e and fixed number of particles ne, what is the most probable set or most probable configuration? That is the general problem that we are interested for the moment. In the case of classical particles, we found that the configuration n1, where n of e1 and n of 2 is 0, n2 where n of e2 and n of e2, n of e is 2, and n3 is, or let's say the 0 to 0 is the most probable, and as we have seen that it is in the classical particle case 0 to 0 was more probable configuration. Okay, so let's write down a general statement as we have seen. So here I'm going to again express my state index as I, and here are my energy states EI, and here is my state degeneracy I'm going to represent by GI, and here is the state occupancy. So now we can say that if I sum the total number of particles, which will come out to be n, and if I sum the total energy of the system, which is EI times Ni is going to be the EI. So here we are generalizing the problem for a large system, and we are looking uh, a configuration Ni where Ni is N1, N2, and so on. Okay, so these are the state occupancy here. This one, so the configuration for which the number, or you could say the multiplicity of microstates is maximum, that corresponds to the most probable configuration, and this configuration is known as or called as equilibrium configuration. What it means that if the total energy E of the system is provided to the system as heat such that it reaches an equilibrium temperature T, then this configuration is the most probable one at thermal equilibrium at temperature T. Okay, so the general problem we are trying to solve is for a given system with this total number of particles and total energy are fixed, what are the configuration for which the multiplicity is maximum? And this is the general problem that we are trying to solve. Okay, so for that we need to learn how to calculate Q of Ni. This we are going to discuss in the next part of this lecture. Till that, thank you very much. See you in the next class. And if you would like to know or read more about this topic, please go to the chapter 10, which is statistical physics, in this book of modern physics by Survey and co-worker. See you in the next class. Thank you very much.